Hello and welcome to the second podcast in the unit on atomic and nuclear physics, standard level unit 7. This podcast we're going to look at electromagnetic radiation and the atom and how these two things interact and how that leads to the most current model of the atom that we're going to talk about. We're only going to look at two assessment statements. And particularly that last one, outline evidence of the existence of atomic energy levels, is what's going to take up almost all of our time. But we will go a little bit beyond our remit here, actually, and introduce a few concepts that will be very useful later on in the course. We're going to start with a question, a slightly different question. We're going to start with a question: where does light come from? Well, let's give an example. The sun, we just saw, was one example. Another example is a light bulb. Both the sun and the light bulb involve heat. When atoms are given energy by being heated, they emit this heat and light in the form of electromagnetic radiation. And if you take light, sun's light, or the light from an old light bulb like that, then you can use these devices, either a prism, a glass prism, or a diffraction grating, to split this light into its components. And here is a photograph taken of a light bulb with a particular filter on, which splits that light, and you can see it into the rainbow. And in fact, a rainbow does exactly the same job to the sun's light by refracting it through and then reflecting it and spreading it out. A rainbow is just the sun's light being split into its components. And in fact, the only reason we can actually only see that part is because that's what our eyes can detect. Our eyes are sensitive to electromagnetic radiation between about 400 nanometers and 700 nanometers. But the actual spectrum extends either way. This particular spectrum is laid out in terms of increasing wavelength. So longer wavelengths include infrared, heat and radio waves. Shorter wavelengths include ultraviolet, X-rays, cosmic and gamma rays. The actual radiation given off depends on the temperature, and this is something else we'll be looking at later. This is called a continuous or black body spectrum. And the wavelengths here on the bottom and the wavelengths and the amount of radiation that are given off by an object when it's heated depend on the degree to which it is heated. So an object heated to 3000 Kelvin, which is pretty hot, will give out a peak somewhere in the infrared. Most of its radiation is being given off as heat, thermal radiation, but there is an appreciable amount given off in the light, more red than blue, so it actually glows red. 4000 Kelvin, there's even more red and also a fair amount of blue and green, so that's actually kind of going towards yellow. And once you get to 5000 Kelvin, the peak is heading towards the middle, and the light is getting to be a more equal mixture of the colours, so that's going to be a sort of yellowish white. So that's where light from the sun comes from. It's where light from all hot objects comes from, such as light bulbs, and that is a continuous spectrum. But that's not the only source of light. We can get light without so much heat, and an example of that is the neon signs here. The device approximately is shown here in the diagram. You take a glass tube and you evacuate it, you take all the air out of it, and you pump in very low pressure amounts of the gas. So low pressure that the individual atoms don't interfere with each other. So they exist, they're around, but they don't, they don't mess each other up. And then you put a high voltage supply across the two electrodes. That gives energy to these atoms and to the electrons in these atoms. And that results in light being given out. There is a point, we'll come back to the models and all this in a minute. So here's a picture of a continuum, a continuous spectrum. But the light that's given out when we accelerate and give energy to these atoms of gas doesn't look like the continuum. Instead, it only gives out in certain specific wavelengths. Okay. Neon. Where's neon? Here's neon. We saw that neon is this sort of reddish, orangey red colour, and that's because most of those, it's got quite a complicated set of different lines, but they're still individual lines, most of them concentrated in the red or orange end of the spectrum. The honest carbon monoxide, by the way, has a more sort of filled-in structure, and that's because it's an atom rather than, a molecule rather than just a single atom of a single element. What's all this got to do with the atom model? Well, here's what we know as the Bohr model of the atom, which we were looking at in the last podcast. Here's an example: aluminium, nucleus in the middle, 13 electrons in different specified orbitals. Okay, now we said in the last podcast that Bohr created his model and said that only certain energy levels are allowed to get over the problem of the fact that if electrons could orbit in any energy level, in any way, they would just lose their energy and just collapse down. Okay, so the Bohr model overcomes that by only specifying certain energy levels. But there is evidence for the Bohr model, and that evidence comes from these emission spectra. Okay, because Bohr said, well, if an electron jumps between these specified energy levels, then it will give out a packet of light, a photon, look at the definition of a photon later, with a certain specific energy. If the electron absorbs that specific energy, it gets promoted to another energy level, and it will then release and get demoted to a lower energy level and release that energy. And he came up with an equation. The energy released equals something called Planck's constant multiplied by the frequency. That's actually not a V, that's the Greek letter nu, which is sometimes used to represent frequency. So the photon of light, the light emitted, will have a certain amount of energy, a certain amount of frequency. There's an equation so good, they even put it on a stamp in Denmark. So h nu equals the change in energy levels, E2 minus E1. So the frequency of emitted light is proportional to the change in energy of the electron. So the electron changes energy, goes down energy levels, it loses energy, and it will emit light. And to give it the modern form of the equation, hf equals E2 minus E1. So F, or nu, equals frequency measured in hertz. H is Planck's constant, which is 6.6 times 10 to the minus 13 meters squared kilograms per second. Don't have to remember that, it's in your data booklet. So, here is hydrogen. The emission spectrum, as it's called, of hydrogen, when hydrogen gas gives off light. And it has these lines. Well, these lines correspond to certain energy changes in the energy levels of a hydrogen spectrum. Two of these sets, going down to the ground state from the second, third, fourth and fifth Lyman series, we can't see those because they're actually in the ultraviolet region. They're outside of our visible range. Similarly, the transmissions from the fourth to the third, fifth to the third and sixth to the third we can't see because they're in the infrared range. But what we call the Balmer series happens to nicely lie within the visible range. So this fairly little gap here between 2 and 1 gives rise to that particular red line there. The bigger gap, 486, gives rise to the green line, and the 434 and 410 energy level changes, nanometer changes, give rise to these sorts of orange and purple lines down here. So the fact that hydrogen has an emission spectrum is explained by the Bohr model of the atom. The hydrogen emission spectrum is direct evidence for the Bohr model. Now, I mentioned earlier that a consequence of this Bohr model is the photon. Previously, we've only ever really looked at and thought of light as being a wave. It has wave properties. It has reflection, it has refraction, it has diffraction, it has interference. superposition. But all of these properties are exhibited in the transmission of light. When you look at the emission or absorption of light, it actually makes a lot more sense to think of light, and light really does act as a particle, as a packet of energy. And these packets we call photons. So a photon is a particle of light. And whenever an electron changes energy levels, delta E, then you have a photon emitted whose frequency is determined by HF. One example in nature of this is the aurora. The aurora here, which are visible at the poles, this is aurora borealis, the northern lights, are caused by charged particles being trapped in the Earth's magnetic field. Now, if you saw the vodcast on the Earth's magnetic field, you know that it sort of comes back down to Earth at the poles. And it carries these charged particles with it. These charged particles hit the gases of the atmosphere and they give energy to the electrons. The electrons are promoted and then they fall back to a lower state and they emit some of their energy. And these green colours are due to oxygen in the atmosphere. Different gases give out different coloured light. So this is emission spectrum stuff. Very good. Let's have a look at using this equation. So what energy change is required to produce red light? Red light, we'll say 700 nanometers. Well, equation E equals HF uses F, frequency. So to find frequency from the wavelength, we use C equals F lambda, rearrange it to get F equals C over lambda. C is the speed of light, 3 times 10 to the 8 meters per second, divided by lambda, 700 times 10 to the minus 9, which is nanometers, gives you 429 times 10 to the 12 hertz. That's the frequency of red light. And then we plug that into delta E equals HF. H, Planck's constant, 6.6 times 10 to the minus 34, multiplied by F for frequency, 429 times 10 to the 12, gives you a total of 2.8 times 10 to the minus 19 joules. This is a pretty small number. We don't like using small numbers, and so basically the physicists said, sod the SI system, we're going to use a different unit, and the unit they use is the electronvolt. Now, you should be familiar with the equation that potential difference equals work done per unit charge in an electric field. Rearranging this, if an electron moves through a potential difference, then it will gain energy. Okay? If you think about a battery in a circuit, then the electrons pass through the battery on the way around the circuit, and there's a potential difference. They gain energy. How much energy do they gain? Well, each electron will gain energy by this equation. Work done equals potential times Q. So if it's 1 volt, then energy change equals 1 times the charge on the electron, 1.6 times 10 to the minus 19 coulombs, to give you a total energy change of, well, 1.6 times 10 to the minus 19 joules. And we call this a unit of energy the electronvolt, because it is the amount of energy gained by an electron passing through a potential of 1 volt, EV. And 1 EV equals 1.6 times 10 to the minus 19 joules. So it's not a very big unit of energy, but it is appropriate, very appropriate, when we're talking about the energies possessed by sort of atomic level particles. This is the equation from before. Delta equals 2.8 times 10 to the minus 19 joules, which is 1.75 electron volts. Much easier to deal with. To give you some idea of energies in electron volts, the average Ke of atom in the air, as it bimbles along at 20 degrees C, is about 0.02 eV, not very much. Red light photon, we've seen 1.75. Blue light photon, more energetic. Okay, higher frequency, shorter frequency, low frequency, shorter wavelength, higher frequency. Yeah, got it. So more energy, 3.1 electron volts. Energy released by one molecule in chemical reaction, 50 electron volts, which compares to released by one atom of fuel in a nuclear reaction, 200 mega electron volts. So looking at electron volts, you can see how much more energy is available in nuclear reactions compared to chemical reactions. But anyway, we're getting away from the point. One other thing is the absorption spectra. Now, we've looked at continuous spectra, which is when we look directly at a hot object. If we look directly at a cloud of gas, then we have an emission spectrum. If we look at a hot object through a cloud of gas, then we have an absorption spectrum. And that's because, as I've said, certain wavelengths, certain frequencies correspond to these energy levels. So as the black body's light passes through this cloud of gas, and then light of those particular wavelengths is absorbed, promoting electrons. Okay, and those electrons then decay back and re-emit the light, but they re-emit it in all directions. So these black lines here aren't actually completely black because a small amount of light is emitted by the gas in this direction, but most of it isn't. So you have a continuous spectrum, you have the emission spectrum looking directly at the gas, and then but looking at a hot object through the gas gives you a corresponding absorption spectrum. And your classic example of a hot object looking through a gas is the sun. The sun's photosphere, the bright surface of the sun, and the sun's atmosphere above the photosphere, which is the light that shines through. And this gives you the solar spectrum. Here we see very spread out the solar spectrum with all these hundreds and thousands of lines in it, all of which correspond to different elements and occasional compounds, but mostly elements in the sun's photosphere, which gives us a composition of the sun. Interesting stuff, and all comes about because of the model. What's going on here? Why is it doing that? Very strange. Hold on. So, going back, is the Bohr model atom appropriate today? Well, there's been a couple of changes. The Bohr model did look like the Rutherford's model, but with just sort of fixed energy levels. Now we know that that's very much a simplification. Instead, we have lots of different arrangements of electrons and how they can be arranged in different ways in an atom. And here is just a few ways that they can be arranged. But we still have the idea of different energy levels. They're not corresponding simply to different orbits, but they still work as a concept of energy levels. Okay, so we've gone through lots of evidence for energy levels, and next podcast we will look at some of the we'll stop looking at the electrons really, and we'll look actually at the nucleus of the atom and what that's all about. Thank you very much.